the, all right. So I suppose you see the previous slides and my mouse well. Is that right? Okay. It's fine. Actually, I like. Don't feel shy. I like to be interrupted and to discuss. All right. Well, thank you very much. And as Hao said, I'm part of the LISN. I don't know either how to pronounce, but this work was mostly done in Brno, so I put my former affiliation. And I also would like to, so I will talk about subspace model for acoustic unit discovery, as the title suggests. But I also would like to acknowledge Bolaji Yusuf, my colleague and accomplice for this work, who has done quite a significant contribution to this work. All right, without further ado, let's jump into the presentation. And here is today's menu. So I will first define the acoustic unit discovery problem, what it is, and eventually what is the motivation behind this line of work. Then I will talk about the state of the art, and this will be a quite subjective part. It's the state of the art as I see it. And then I will talk about subspace model for AUDs. I will enter maybe the more interesting part of this presentation and eventually report some proposal of work, or let's say proof of concept, for the task of discovering units. All right, so acoustic unit discovery, so what it is, it's a rather easy to define task where you are given a set of recordings, and this recording don't have any labels. So you just have the audio. This set of recordings are from the same language. And your task is to learn an inventory of phone or pseudophones. We call them acoustic units. So concretely, you have, let's say, this bunch of recording, and you will learn, let's say, a bunch of indices. Let's name AU1 till AUN. And for each of these recordings, you will learn some embedding vectorial representation that encodes the characteristic of the phone. So AU1 is a name, it's just a label, and the representation or the characteristic of the sound is encoded into a vector. In addition to this, we also want to provide a labeling of our data. So for each of the utterance, let's say for this one, we also say that, okay, now we have this utterance, and this particular segment is actually acoustic unit number 13, and maybe this one is acoustic unit number 22. So we need to find an inventory of phone, and then we need to label the data and provide a time alignment of the data. Put it in another way or perspective, you can think of it as learning, loosely speaking, like a baby. So here the task is not to discriminate between already known categories. The task is more you have some sensory input, speech, and the system has to find a structure within this input. So here the structure we hope to extract is a phonetic structure, like a baby learning to speak. So this is a very approximate model, but I think the metaphor suits nicely. All right, so this is a task, but why there is some interest in this effort? I think there are many interests, but I see mostly three of them. The first and foremost one, is the documentation of endangered languages. So we are facing at the world level, at the global level, a diminution of the language diversity, and we are lacking of field linguists. We are lacking of resources, basically, to documenting and revitalizing these disappearing languages. Think of the ASR or any speech technologies nowadays can only be built using a significant amount of transcribed data. But most of the data don't have these resources of transcription, and some languages are not even written. So how can we provide tools for these languages? So that's one objective of the unit discovery. If we could just simply learn a phonology of a system and eventually services or technology based on this core technology to help the documentation and the revitalization of languages. Another interesting aspect also is the relation between, or the correlation between human learning. I was mentioning as a metaphor, as an image, between AUD and learning like a baby. Well, some people see it not just as a simple comparison, but as a really practical simulation, where instead of studying directly humans or the brain, because it's very hard actually to design experiments to investigate how the brain is functioning, we cannot simply open the head of someone to see what's going on in the head. So a lot of people actually, or neuroscientists, bear the hope that machine learning techniques can provide a nice simulation environment or tool or framework, and they can learn principles about human learning from machine learning. Lastly, and this is related to the documentation of endangered languages. Nowadays, state-of-the-art or mainstream machine learning techniques rely on the paradigm that we have a lot of data. Even not transcribed, we still do assume a lot of data. For endangered languages or low-resource languages more generally, this is not true. If you have a few hours of data, of speech, that's already a lot. 3-4 hours of data may sometimes consider a lot. So we need to learn to design new machine learning algorithms which are not data hungry. That's actually more data efficient. From much less examples, they can still generalize well and be of significant use. So that's the main, I would say, motivation of this type of learning. So acoustic unit is a type of unsupervised learning. It tries to find the phonology of a language, and we hope to help the documentation of endangered languages or low-resource languages generally, to provide some computational model of learning, of human learning, and also to provide new machine learning algorithms which are more data efficient, something like zero or few-shot learning. All right, so now let me go through a state-of-the-art, and let me emphasize that this is a personal thing. So I don't think there is an established state-of-the-art, so I will simply say what I believe is the state-of-the-art. A very, very brief and biased history. So this idea of unit discovery is not new at all. It's 30 or more than 30 years old. And the early models, most of them, some started end of the 80s, were mostly based on what I call heuristics. So they had a set of rules, of processing rules, and given these rules, they were able to provide some units at the end of the pipeline. Most of them were based on some version of the algorithm of the dynamic time warping algorithm. I'm not criticizing them. I'm not saying these were bad systems. Some of them were actually quite clever. If I want to qualify them, I would say that they were lacking a theoretical framework to really establish themselves as a complete discipline. Then, starting from the 2000, started the non-parametric Bayesian-based model. And this model were actually taking some idea of the previous model, but providing suddenly a well established and well not documented, but well understood framework Bayesian machine learning for this type of problem. And these models are still actually used. So I probably need to correct, and this is 2021. And in the recent years, we have also seen a more and more neural network-based model trying to achieve this task. So let me first start with a very brief description of neural network based model for AUD. I just list a few, and actually every year there is a lot of people working on it. So there are a lot of very quick pace of the field makes every year sees a lot of new models. So I just list a few, but most of them are based on this following principle. You have some X is your input, of course, and you have some encoder. And then you have a quantization layer, which can take different form. And because you don't have any supervision, you need to somehow, to complete the learning, you need a decoder. And so that will be a decoder. And the decoder tries usually to reconstruct X in some sense. So there are very variation of this objective function. There is the traditional mean square error and some more advanced objective function like contrastive predictive coding. The quantization also might be different. For instance, the VAE HMM use a graphical model for quantization. VQVAE use more simply vector quantization. At the other end of the spectrum, I was mentioning this non-parametric Bayesian-based model. So they all stem from the work of Sharon Goldwater, which in her thesis actually proposed to use this model for solving the following problem. You have text, but this text is not segmented. So you simply have a sequence of letters of, let's say, English text or any language text. And she shows that this model can actually be quite efficient at segmenting the data. So instead of you give this input to the system, and after analyzing a lot of sequence of strings, then the model tells, well, most likely this should be written like this because I've seen this word pattern several times, and so on and so forth. So that was in speech or in language processing, that was, to my knowledge, one of the first successful utilization of non-parametric Bayesian techniques. Later on, Chia-Ying Lee and Jim Glass from MIT combined this model with acoustic ideas. So they reuse the same idea from Sharon Goldwater, but combine it with an acoustic model to process not text, but speech. And they were able to have a first AUD, or let's say the first working AUD technique. Take it with quite some a quote, please. And maybe it's not as drastic improvement, but I started to work on AUD in 2016, and I was basically, I proposed some optimization of the MIT model which is the same model, but as a more efficient training based on versional base. I won't enter much into the details of this HMM baseline, but for the sake of the presentation, I will give you a gross idea of how it works. Say you want to learn the AUD from this, from an utterance. The crux of the idea of the model is to decode this speech with the following decoding graph. So you start from starting state of your decoding graph. You assume there is silence at the beginning and end of your utterance. And then in between, you can basically jump from any units in the order you want. Imagine that each state here can be replaced by another 3 states HMM, the traditional HMM-GMM model for speech. So each unit has this particular structure, and the model is simply trying to decode speech using this following structure. There is a few peculiarities. Let me mention one. Because the model is non-parametric, it uses Dirichlet process. The number of units is not finite, at least theoretically. The model assumes that you have infinitely many acoustic units. However, during the inference, the model learned to assume that the probability to go in some units becomes negligible. So practically, there is a truncation happening somewhere, but this is learned by the model. So in a sense, one of the strong quality of this type of model is that it learns the complexity or the number of units directly from the data. It's not some hyperparameter. All right, so I briefly revised the major trends in this field. I will now introduce some evaluation metrics, the one I use, and we'll start to compare to see the different baselines. So I myself like to use two types of metrics. One to evaluate the clustering, how good how consistent will be the clustering of the segments discovered. Are they mapped to the same phone if they belong to, or to the same unit if they belong to the same phone? This is measured with a normalized mutual information. And it's a statistical measure with some renormalization constants such that if there is a one-to-one mapping between acoustic units and phones, then the score will be the highest, will be 100%. On the contrary, if there is no relation or no relation at all, or no correlation between the acoustic unit and the phone, then the score will be the lowest, 0%. Importantly, because of the normalization denominator, if the system learns a consistent clustering but too many units, it will be penalized. So the only possibility to reach this peak is to have really a one-to-one mapping. Having more units than phones is necessarily penalized. The other part of the metric, or the other metric, is regards the segmentation. So on this, imagine that we have an iterand. This is a reference phones, and this is a hypothesized transcription of the AUD system. And we'll count how many boundaries were correctly guessed, how many were missed, and how many were falsely detected. And we'll compute the traditional precision and recall, and we use the F-score metric to combine them. For all the experiment of this presentation, I report numbers on the three languages, Bosche, Yoruba, and English. Bosche is a real case of endangered language. It's spoken in Congo-Brazzaville. And it's a corpus which has 3 to 4 hours of data, but quite significant amount of silence. So it's a little bit hard to really build something from it. Yoruba, it's not an endangered language. It's spoken by millions of persons. However, it's low resource languages. So low resource doesn't mean endangered, just means that don't have a lot of resource. It's mostly spoken in Nigeria and West Africa in general, but also in Brazil. So it's quite a global language. And finally, English, the traditional TIMID, this is for control experiments. Rest assured, English is not endangered languages. The feature-wise, it will be always the same for this presentation, only the traditional MFCC features. All right, so the first comparison I will make is between the VQ-VAE. So this was one model from an adapted version of Jan Chodowski model. We needed to adapt it because, of course, to use or input the MFCC features, and also we needed, in order to achieve this result, to drastically reduce the number of templates in the quantization layer. So these 50 numbers here were tuned to improve the mutual information. This number of units from the HMM-based model was learned automatically. So observe that both systems are performing. They are well above chance. Chance is 0% in both metric. However, we observe that the HMM is much stronger in terms of clustering, but also in terms of segmentation. So it seems that the HMM-based baseline has a better clustering capability and better segmentation outcome. Visually, it's relatively easy to see this. So here you have the output of the HMM on one utterance of TIMID. Here the utterance says cement is measured in yards, probably with a better accent than mine. And the low axis here, the bottom letters are the English, the TIMID fonts, And on the upper part of the figure, these are the acoustic unit indices. The black line correspond to the reference boundary, and white dashed lines are the hypothesized boundaries. So we see that the HMM is providing some segmentation, far to be perfect, but somewhat related to the segmentation, to the phonetic segmentation. We see that the VQ-VAE is struggling already. He has some segmentation which seems to be nicely discovered. However, he has very many spurious boundaries. So in many parts of the speech is actually over-segmenting, and that actually decrease the matrix. The next comparison is another neural network-based model, which is VQ-Wave2Vec, and this one was trained on almost 1,000 hours of English data. And we compare it, so we simply took the pre-trained model and applied it as it is on timid data, so we didn't retain it ourselves. And we observe in this case that the NMI is much better, HMM is slightly better, but I don't think the difference here is that significant. However, the segmentation is much better for the HMM. Observe also that the number of units for both systems, it's two variants of the same system, have a much number of units. Here we are talking about 10 or tens of thousands of units, whereas our system is simply having less than 100 number of units. And if we look again visually what the system is learning, we see that it's quite different. Once again, the HMM discovers some units which are a little bit correlated with phone, not perfect, but hopefully correlated with phones. The VQ-Wave2Vec, however, is almost assigning for each frame a particular cluster. So that's why it's actually having a lower number, lower score at the matrix. The fact that he achieves about 35% NMI means that he's learning relatively consistent clustering, but is encoding too much information, probably speaker, channel, and so on, that actually makes penalize it with the metric I have chosen. Lastly, we compare with another model from MIT. This is ResDaveNet. This is not a fully unsupervised approach. This is what I call a lightly supervised model, where you have speech as input, and the task of the network is more or less to find an image. I'm simplifying here. So it's just like if we replace the text transcription with some image, and the audio describes the image. Maybe the audio is kids are playing football, and you have a picture of a football field with children playing. So this is we have that two quantization layers in this network. So we have measures we have made the comparison with both of them, and we see the NMI is actually comparable in both cases. And the ResDaveNet has a much better segmentation than previous neural network models, and slightly above the HMM case for one of the layers. So it seems that the ResDaveNet is actually outperforming the other neural network with this. Looking at the segmentation, so of the second layer, the one achieving the best segmentation, we see that actually the segmentation is a little bit irregular. Sometimes he's finding good boundaries, but it seems that he has also, the segmentation is not so phonetically related, at least visually. The other quantization layer also suffer from this over the high frame rate happening. Of course, this system is performing better than other neural network, but it is also aided by the images. All right, so that will conclude my state of the art. So I just want to clarify one thing. I am not trying to say that HMM is better than neural network. It's not exactly my point here. What I would like you to realize is this is an unsupervised learning problem. More particularly, this is a clustering problem. And neural networks are extremely powerful for discriminative tasks. That's a fact. much better than HMM for this, for instance. However, neural networks are hard to use for clustering problem, even simple one. And in this case, GMM, HMM, or simpler model are easier to tune to get the cluster you actually want. So I think here what we observe, the benefit of HMM over neural network is mostly due to this. It's a model which is a little bit simpler than neural network, but its simplicity allows us to use it more efficiently for the clustering task. All right, so we have established that HMM is not a very good model, but at least it's quite competitive in terms of clustering with existing models. How do we improve it? And we now come to the more interesting part, the subspace model idea that for acoustic unit discovery. So it all comes from some thinking over some psycholinguist findings, which I understood in the following way. Infants at birth are sensitive to speech. So it's not like they are born and they know nothing about speech. The same studies show that they have some sensitivity to speech. They are able to distinguish between human sound and not human sound, and also they are able to distinguish between sounds that allows to discriminate between phones. So to make it simple, I have no rather strong French accent, but at birth I was not French. I didn't have a French brain. I had a human brain. And I was, however, sensitive to human languages. And because I was living in a French environment, I started to learn to distinguish more carefully French sounds. And meanwhile, I become less accurate at distinguish phone nuances practiced in other languages. So I became basically a French speaker. So the important things are this innate sensitivity to human languages and also adaptation. So it seems that infants have some information hardwired through the evolution process. And they have also a ability to become specialized, basically. It's not everything is hardware, much is learned, and they're able to overcome their pre-wiring information. This is their pre-wired, pre-given information. So starting from this observation, we saw that maybe we can actually follow the same, try to endure a system with similar capabilities. We first saw that maybe we can give similarly an innate sensitivity to our system. So giving information to our system at first, not to let the AUD system learn from scratch, but tell, well, this is a phone. Let's tell our system, this is a phone, and try to find other phone on target language. And also we want to, so let me label it 1. And number 2, we also want the AUD system to be able to specialize to a language, because we acknowledge the fact that we cannot have a universal system and each system should be specific. So the system, the AUD system, should be able to adapt itself to the language. The number 1 was basically addressed, the point number 1 was addressed in the subspace hidden Markov model during my thesis. So here is really to give prior information to the AUD system. The point number 2, the specialization or the language specialization of AUD system, was done by Bolaji, is here with us, during his stay in Brno. And so let's go for these systems. To explain the subspace hidden Markov model, I need to be a little bit more specific about how to learn an acoustic unit. Let's say that we are given a segment and we are thinking, okay, to which acoustic unit this segment, we need to map this segment. First of all, we need to give embedding a vectorial representation. So the way we do it is we learn the posterior distribution of the data, this is X, and we learn the distribution of the vector representation of eta given X, where this vector representation is simply the parameters of the acoustic model, the HMM of the units, stacked in a vector. So just imagine that this state has an emission which is a Gaussian mixture model, having weights, means, and covariance matrices. We take all these parameters, stack them into a very large vector, and do the same with other states and stack all these intermediate vectors in a very, very big vectors, and that gives us our vector representation. So the whole question of learning a unit is really to answer this question: what is the probability of eta given x? Following Bayes rules, we know that this is simply given by this product, where we recognize the likelihood. This is given by the HMM, no worry about this, and this prior. And this prior will be our concern for today's talk. So let's be a little bit more explicit about how things are going on. First, we have some input, this is x. And through some mechanism, we'll map this input to a point in this space. And so that corresponds basically estimating the parameter of the model given this segment. And then these points represent the parameter of HMM. So implicitly, it represents a sound. So let's say that this point in this space represents R. And this prior has the task of telling if this particular vector is a good or a bad candidate for an acoustic unit. So here, this is R, and I'm asking this prior, I'm weighting it and say, is R a good or a bad candidate for an acoustic unit? And depending on the answer of this prior, depending on how this function will weight these particular embeddings, it will change my posterior distribution. So it will change if this particular vector is likely to be an acoustic unit or not. So one problem with the HMM-based model is that this prior was designed in such a way that it was always saying yes. So if I have the R sound here and I ask my prior, is it a good candidate? The prior say yes, no problem, you can use it. But if I make a prior and, if I get a new vector, let's say here from another bunch of data, and this sound represents, let's say, white noise, shh. Right, shh is a good, it could be a phone actually, maybe a knock. And I ask the prior, is it a good or a bad candidate? Well, the system say, well, it's a good candidate, go ahead. And that we already quickly see, we already see that this is a problem. So this prior was designed to be non-informative. It didn't have information, so it simply said everything can be a candidate. The idea of the subspace HMM is to fix this and to provide an informative prior. We assume the following, it relies on the assumption of the following structure of the parameter space. So this is a parameter space, or the sound space, if you prefer, and we assume that there is a manifold or a nonlinear subspace. We use subspace for simplicity, which encodes the phonetic variability of a language. So let's say that this is my vector of, let's say, A, of the sound A, and it's living here. If I take this vector and move it along the blue lines on this manifold, then I get a new form. So let's say O, and if I move it further, then I will get a consonant or something very different. On the contrary, if I move in a direction which is somewhat orthogonal to the manifold, I am not changing the nature of the phone, so I'm not changing from A to O, I'm staying in A, but I will change I assume that I'm changing the characteristic of the phone. So from A, I will move to, let's say, a high pitch A or low pitch A. So the phonetic subspace represents the phonetic information. The other potential subspace eventually encodes some variability factors such as speaker, channel, emotion, and so on and so forth. So practically here, the goal is to define an informative prior which constrains the acoustic unit embeddings to be in this phonetic subspace. So we basically introduce a new low-dimensional embedding, H, which through a nonlinear function which basically is a subspace, will give the final complete acoustic unit embedding. Visually, this looks like this. So you have the phone, or while learning a phone, so you have some acoustics. You're learning the parameter of your HMM, which will project it somewhere in this space. And because the prior is saying everywhere outside outside the subspace area has a probability of 0, so it's impossible, all the acoustic units are necessarily discovered within this subspace. So they have no choice than to be on this subspace. So now if I have the, let's say, knocking sound, which happens here, well, this won't happen. So the system won't allocate it as a unit because it's not on the subspace. So that's the crux of the idea of the phonetic subspace. And since the beginning, I'm merely assuming this is known. This is not true, and that's the problem. The phonetic subspace is, of course, an assumption, and it's not known. So to somehow use this idea, what we do is we introduce a supervised training stage of the system. So we'll use data for which we have transcribed data. So let's say that I want to learn a Mboshe language. I will use other languages for which I have the phonetic transcription, French, German, or maybe closely related languages to Mboshe. And from these languages, I will learn the parameters of my phonetic subspace, this W and B. And this is done using variational Bayes inference, so the same objective function that all the models are optimizing. So it's, let's say, a minor change to the system. And using this super phonetically transcribed data, I'm learning the phonetic subspace. Loosely speaking, in this training subspace, the training stage, the system is using transcribed data to learn the notion of phone. In the second stage, so here we are not coming to the unsupervised learning. So now we are using the data of the target language, which is not transcribed. In this stage, W and B, the parameters of the subspace, are fixed. And the only thing we are learning are the embeddings of the acoustic unit on the target language. The training, once again, I didn't go through the training, but eventually, if you want to shape your mind, this is a type of EM algorithm. So I had prepared some presentation. I will see if I can. Yes, perfect. So. All right, so let me just explain what you're saying here. So right now, this represents the supervised learning phase of the model. And for the sake of the example, we are learning the phonetic subspace of English. So we are using just English data to learn the phonetic subspace. What you're visualizing here, this 2D space, is a phonetic subspace. So we chose the dimension to be 2 to be able to visualize it. And bear in mind that this 2D space is actually living in a very high dimensional space. In this case, about 5,000 dimension. So it's a very low dimensional space in a very high dimensional space. Every letter that you see correspond to the phone embeddings, and we color them according to their phonetic categories. The system didn't know the phonetic categories, so the colors are just like for visualization, but it was not aware of this information. So I let run the learning, the visualization of the learning. All right, so the space is structuring itself, and we actually observe that the phone of the same categories, or the embedding of the phone of the same categories, are getting together, basically. So the important things to remember is that this phonetic subspace somehow encode a continuum of speech where neighboring embeddings that are close together are phones that are perceptually similar. All right. So back to the presentation. So now the experimental setup for the experiment, for the result, is the same for the target languages. So we are using the Mboshe, Yoruba, and English as target data. And for the source languages, we are using 4 languages, European languages, French, German, Polish, and Spanish from GlobalFound. We made sure that they had about the same amount of data as the target data. So remember that the idea of the subspace HMM is to bring information to the system before to observe the data. So this is some a priori information. And we see that if we simply run the AUD of the HMM without training, just after the random initialization, then we see that we are about chance level for all the languages. If we do the same with the subspace HMM, we clearly see that actually we are well above chance level, both in terms of clustering and segmentation. So that was a nice thing to observe, is like the subspace HMM is able to bring information a priori to the system. After training, of course, both systems will improve. The HMM will reach the level we have reported before on clustering and segmentation. And we also see that the subspace HMM strongly improve and have a significant improvement in terms of clustering, as well as in terms of segmentation over the HMM. So importantly, the subspace idea is not only an initialization technique. It's just not a smart initialization. Even if we were somehow making sure that the HMM and the SHMM are initialized to the same starting point, the training would probably lead them to different solutions. The SHMM is constrained because on the AUD clustering, the subspace is fixed. So the discovered acoustic units are constrained to live in this subspace, whereas the HMM is completely unconstrained. Interestingly, if we say we try to naively specialize the subspace HMM on the target language, that is, we start to adapt the phonetic subspace using the target data, we get a hit in performances for the clustering and also for the segmentation. So this naive idea of retraining the subspace is actually not such a great idea. And that makes sense, actually, because doing so is simply allowing the system to forget the information we have given to the system. So it's natural, I would say, that we don't get improvement, but rather a degradation of the result. So that brings me to the final part of the presentation, the hierarchical subspace HMM. So we have so far assumed that the phonetic subspace is something universal. So every language follows the same phonetic subspace. So there is a phonetic subspace where all the phone of all the language lives. Well, that's quite a strong assumption, and maybe we could make a weaker assumption by assuming that all the languages have a unique phonetic subspace. Doesn't mean to be radically or drastically different, but yet it will be different, sufficiently different to allow different type of phonetic variation. So that's maybe, let's say, English phonetic subspace, and maybe Yoruba, and maybe, and that's the next slide. So we still want to design an educated prior, but we now want to add one more to allow basically to learn the subspace parameter itself. So we need to basically add a prior over the former prior, so the model becomes hierarchical. Don't worry, I will try to explain it a little bit better. Importantly, we are introducing a new embedding, and this is a language embedding. This alpha, it's one embedding for each target data. So if I have, for each target languages, sorry, and this alpha will encode the language itself. Then using this alpha, we will combine it to form the parameter of the subspace. We use this alpha to build the phonetic subspace of the language, and then we use the acoustic unit embedding and the phonetic subspace as before to build our final acoustic unit embeddings. So everything is good. Let me re-explain the same thing, but visually it's maybe a little bit more easy. So we have, here the idea is to build a phonetic subspace which is language specific. So instead of having one phonetic subspace, we have template phonetic subspace. Here I've illustrated for the illustration, I've set two, M1 and M2. So these are assumed to be known. And we say that every phonetic subspace of any language can be described by a combination by a weighted combination of these two subspaces. So I can have a specific alpha, let's say for English, that will give me a weighting of these two matrices, of these two subspaces, sorry, and that eventually will give me this particular subspace. And maybe if I find an alpha for Mboshi, then I will get a new phonetic subspace corresponding to the Mboshi phonology, and similarly for all other languages. So somehow the prior information that we are giving in the phonetic subspace before, now we give it to this basis or this hyper subspace model. So the information is provided at a higher level, and the system is endowed with a new parameters, which is this language embeddings, which will specialize the phonetic subspace of the language. The training is the same as before, basically. The hyper subspace, the parameter M, are not known beforehand, of course, so we need to learn them. And for this, we use, again, phonetically transcribed data. But this time, each language we use in our supervised set have its own particular alpha. So the phonetic subspace, there is no phonetic subspace shared across languages. The optimization learning is done by optimizing the same objective function. I won't go over it. And it's still the same type of EM algorithm. During the second stage of the training, now we don't fix the phonetic subspace. Of course, we fix the hyper subspace parameter. So M parameter, the phonetic templates are fixed. And the only thing we learn is the weighting alpha. So we learn how to combine these phonetic templates to form a phonetic subspace. And we also learn the acoustic unit embeddings as before. And another illustration. All right. So here what you see is the alpha space. So this is a 2D space, again, living in a high dimensional space. And for the sake of visualization, we have only two in practice. We have 5 to 10 dimension. And each letter represents the position of an embedding of a language. So here what you're observing is not the acoustic units, but the language embeddings. The language embedding, sorry. Notice that here we have splitted each language into different splits, and the system believes these are different languages. The purpose of doing this was to verify that languages that have the same acoustic will be mapped together, and we observe this is true. So this is the training, the supervised stage of the training, and is learning some organization of the acoustic units, of the phonetic space. Now, this is the second stage of the training. The phonetic subspace, the hyper subspace, sorry, is fixed, and we are now learning the language embedding of the target data. So now the learning is unsupervised, and we have several templates for several embeddings because we have several runs, sorry, of the algorithm. Observe that because the learning is unsupervised, there is quite a lot of uncertainty in the answer, and this is also because we have quite some uncertainty. The system does not push them as far away as other systems, which are supervised and much more certain. All right. So I'm almost finished. So I'm thinking a little bit late, but I'm finished in 3 minutes, I believe. So the experimental setup is the same as before. We have the 4 languages from GlobalFound used to estimate the hyper subspace of the system, and then on the target language, as I was saying, we learn the language embedding on the acoustic unit. We use the same target languages as before. Just to recap the story, we started from the HMM baseline, this somewhat old baseline, which gives some clustering and F-score score. And we saw that the subspace HMM can bring a strong and drastic improvement on different languages in terms of clustering and segmentation. We also saw that if we naively try to tune the phonetic subspace of the previous model, we actually decrease the performance. We cannot simply tune the system. We need to constrain into sensible way of adapting the phonetic subspace on the target data. And this as a result of the hierarchical subspace model, where we see that these models are all language specific, and yet they do improve over the subspace HMM in terms of clustering and segmentation. We do have, well, I would say it's a very tiny drop here. I think the system are quite equivalent in terms of F-score. These are some statistics, and I will share I will send the slides to Hao if he wants to send them. So I won't comment them. I'm running out of time. And this is just a visual example of the difference of the system at the end. So this is the HMM example I was showing earlier. So we have some segmentation. And we already see that the subspace HMM has a much more pleasing segmentation, which does have some issues sometimes, but looks much more accurate in this segmentation. So hierarchical subspace HMM has actually a very accurate segmentation, sometimes near perfect, with some spurious boundaries from time to time. So that brings me to the conclusion, and well, the classical thing. So we have proposed new models or a new principle, basically, which is this idea of subspace model for unit discovery. Here we have proposed a classical subspace hidden Markov model, and we have proposed one variant, which is a hierarchical subspace model. And we can imagine actually many more variants, including speakers, speaker viability, or other type of viability, to actually start to add more and more information into the system. Interesting note, we started actually from observation of how humans or infants are learning, or at least how we believe they are learning. And we observed that replicating this behavior was actually beneficial for us. So this is rarely happening, or this rarely happened in speech. So I thought it was interesting to mention it. Or maybe one very important point is this one, which I made the whole presentation using subspace hidden Markov model, but it's also important to realize that the concept of subspace, hierarchical subspace, is absolutely not tied to hidden Markov models. It can actually be used with other models, a very wide variety of models, actually. So you should not restrain yourself of thinking, okay, this is with HMM, I won't use it. Actually, the principle will be the same for a wide variety of models. If you're brave, I encourage you to visit this repository, which basically is the implementation of all the models I have presented here. This beer project is currently under re-implementation in Julia, so the repository is not active anymore, but it actually contains still the implementation of this model. So I think it's still of value. And what about the future? So I suppose you all realize that future in a COVID time is a little bit a strange word. It's hard to see how things will be tomorrow, but at least for AUD, I think I know, at least I hope I know. First of all, AUD is not a solved problem, and even with our best system now, I don't consider that we have a system which is working sufficiently well to be practical. I think we are getting there. We have made strong improvement over the time, and we are at the boundary where we will have something which suddenly can be used soon in the wild, but we are not there yet. Many problems need to be solved. The two major ones are probably the acoustic modeling. So a better acoustic modeling means better cluster, means having a more better phonetic subspace, because the nature of the subspace also depend on the type of model you choose. And if you have a more accurate model, then your subspace will model things better. But also the language modeling, which I didn't mention at all in this presentation, but is also important. Discovering acoustic unit is not an end. It's not, once we have the acoustic unit, what happens? So it's the first step, it's necessary, but we need to go further. And one step further is words. So now we have the phones, or we have some phones. How about more structured patterns inside this sequence of phones? And that will be syllables or words. And if we were able to basically solve these two problems, which are basically definitely not insolvable, but rather reachable in the near future, I think we are very close to the first systems that would truly learn speech as humans. And I will leave you with this optimistic words. So I just put some references in the slides, and just quoting myself, I like to quote myself. And I thank you very much for your attention, and I'd be happy to answer your question.
All right. Thank you so much for the presentation. Well,
thank you.
If anyone has questions, feel free to unmute yourself.
Hi, Lucas. Thanks for a very good talk. I just wanted to ask you a very quick question about some of the prior work that you mentioned. So in particular about the neural network-based approaches. So when you were comparing the HMM-based approach and the neural network-based approach, can you comment on whether there was any form of a prior on the duration of acoustic units used in neural network-based approaches? Because in case of HMM, you have 3 states, right?
Yes.
Which had quite a strong prior on what you should get. Whereas I'm not that familiar with these neural network approaches. I was just wondering if you can comment a little bit on that.
Yes. So well, that's a very nice question, actually. And I should mention that the neural network field is moving so fast that even this presentation is maybe 4 or 5 months old, it's already a little bit outdated. So none of the models, the neural network models are actually using, are having a temporal prior on the units. And I think this is what they suffer from. I mean, clearly you see this, these settings here, they don't have the constraint that a unit should have a minimum duration. So since then, there have been some attempt to impose these constraints. So one of the attempts was, I'm sorry for jumping, this one. So the VAE-HMM, it's actually not so recent, this one. It's a versional encoder, which has a HMM-based AUD model as a prior. So this one is actually quite nice because it combines both worlds. The downside of this model is it's quite complex, and I'm not aware of anybody who replicated it beside the Paderborn team who did it. Another neural network that I did not mention because we are still trying to compare with is one from Herman Kemper, actually our Herman Kemper's team, where they have some, so they use some, if I understood well, maybe Herman can comment on this if I say something wrong, but they have some quantization layer as any of this model would do. And then they have some extra constraint, or let's say post-processing stage, where they will basically enforce the constraint that a unit cannot last 1 frame long, but should have at least some duration. So I think there are quite some ways to combine this, but the comparison I'm using, actually, none of them were having this temporal structure.
Perfect, thanks. And if you don't mind, I had a second question now
of
about
course.
the approach that you described. You mentioned that you were looking for 2 kind of forms of variability. So one of them was the phonetic one, and the second one was the speaker one.
Maybe
phonetic and then the speaker channel one.
It was just for illustration. I don't, in practice, I'm trying to find the, So in this speaker, it's only for visualization. In practice, I don't model this one, the red one.
Right. Perfect. Sorry, I just wanted to make sure that I didn't miss the important bit there. Perfect. Thanks.
Oh, that was your question. Okay.
Yeah. Sorry.
Hi, Lucas.
Hi.
Also, thanks for the great talk.
Thank you.
In a perfect world, you have phonemes that have perfect boundaries, and you can compare them. The world isn't perfect, and this assumption that there is this fixed boundary between phonemes doesn't always work. So you sometimes glide from one phoneme into the other. You have context-dependent phonemes. So basically, what's your take on that? And do you impose some kind of strong prior on that kind of assumption if you base your evaluation on that?
Right now in the evaluation, no. I think the evaluation is simply comparing what the reference transcription is, what the hypothesis is, and tries to make out of it. But I think your question makes a lot of sense, actually, because there is a context-dependent phone. I mean, there is co-articulation, even if we don't perceive it, like physically it happens. And I think all the bias of the old HMM models are actually here in my model. So, and there is no denial of this. And there is the problem actually of having a little bit of basically ignoring this contextual information. It's probably not such a big problem in a sense that it can be fixed in several ways. So you mentioned having context-dependent phones, and I am not very happy about this because that makes things way more complex. Right now, we are trying to learn the number of phones, and if we are basically looking for something between 0 and 100. I mean, between 50 and 100 phones or 200. If I start to look for triphones, it's probably 100,000 or maybe, I don't know, million, or it would be a different order of magnitude. And that's not possible at all, because here, in a traditional decoder, the word give a constraint, so you can somehow optimize your decoding graph. Here, you're trying to cluster, so clustering triphone would be hell. However, we can, in my opinion, I think we can still bypass the issue by the at the feature level. So right now, what is happening is this is your utterance, and you have the traditional MFCC frames, which captures about 25 milliseconds of context. Well, if you simply take several frames, right? You define a window and you build a new set of features that will encode this. Like a TDNM. I'm making things way more complicated, but it's just like a TDNM. Just imagine that you build a new set of features, and each frames actually represent a span of, let's say, filter bank or MFCC. Basically, your input feature to the HMM will be simply have more context. And you can even process them with a neural network to have discriminative features, and this type of thing. So just by processing the input to your HMM, you can start to have a clustering model that still work at a frame-by-frame basis, but each frame will actually represent a much wider context, not just 25 milliseconds of speech, but maybe 200, 500 milliseconds. And in this way, I think that we can definitely model this co-articulation or context-dependent phones. Maybe some units actually may also capture these context-dependent phones already. Maybe we have some units for A followed by B and A followed by C, for instance. It's already maybe happening in this way. These are just suggestions, and maybe they are very naive, but I firmly believe in them.
Okay, my question was more the evaluation side of things.
Okay,
I mean, there is a way out. I mean, you surely came across ABX.
Okay.
Have you tried it, and do you get the same correlation? So, do you get the same results in terms of what model is better than the other?
So I did try ABX, and okay, I'm not a big fan of ABX. I should be honest about it.
I am.
That's okay. I will just tell you a concrete example where I basically decided to abandon it. It was actually in the workshop 2016, And we add a GMM system. So GMM is simply a special case of the HMM type of model. And we observe actually that doing the GMM clustering give a much higher ABX, whereas if you look at the mutual information and other metrics, is much worse. In my opinion, it makes more sense that the HMM performs better simply because it has actually the temporal structure that someone else was mentioning. So for me, it was really a sign that the ABX is not eventually measuring what it should. That's, let's say, empirical observation I have made. Then one criticism I have with ABX is a complete, you cannot just have a matrix where you choose your distance function. I mean, how can we make sure that we're comparing the same thing? So if I choose a distance function with, if I decide to have a ABX for MFCC and I choose a Euclidean function, and then I have my representation, let's say my discrete representation, I use that, I don't know, KL divergence or I forgot the name of minimum length change. That's a completely different metric. So we start to compare things which should not be compared. I understand the ABX principle, and I think the ABX is nice for when you try to evaluate a system. You want to have, so the system here might be eventually an inference or anything which basically gives some inputs and given some input, gives some output, and it acts as a filter. However, here the ABX as used by the zero resource challenge is not in this spirit. It's trying to, I don't know, actually here, honestly, I don't really understand the ABX as used in the zero resource challenge. So it's a little bit hard for me to comment on it. But I feel that you're you like this matrix very much. So I'm not very satisfied with me because I don't have the feeling I give you a very nice answer.
So maybe I can say a few words why I like it.
Sure.
The thing I like most is basically that it is agnostic to a couple of assumptions. So if you compare yourself to hand and manual labeled phonemes, or sometimes in these data sets, these phonemes basically come from an alignment from speech recognition, you have this prior assumption that this is a good representation. That this is a good discrete representation. Maybe that's the case, but then you're basically missing out on all the other representations. There are other possible ways to discretize this. So in being completely agnostic to that, and also allowing to compare soft clusterings. So another representation, segmentation would be that you don't have a discrete unit, but you have a posterior over all the units that you have, and then you have that posterior for every frame, and that would be very similar to the posterior of the neural network in a DNN HMM model, for example.
So we did this. We did this actually for the zero resource challenge, and actually we have ways to tune. So what we do, we don't output the sequence of tokens, and we output the posteriors, and we usually use the KL divergence metric. And so actually we have a way to tune it. If you want to get good score on ABX, we simply have to have some scaling factor to smooth the posterior. So as long as you do this, then you will get very good ABX scores. I understand your argument, and it's actually a nice one. I think the ABX, there were good intents behind the ABX, trying to say, of course, we have something agnostic. And at the end, what is important is to actually make sure that we can discriminate between, let's say, two phonemes, basically. I am a little bit concerned about the implementation of the metric, shall I say? And so I mentioned the choice of distances. One problem also is like what happens if you have you can label each oh no, sorry, that won't happen. If I was just thinking in terms of can the metrics can also be penalized if you have too many units, for instance, if you label every vectors, but that would actually be penalized.
I mean, there are these bit rate comparisons that would directly
Yes,
Yeah,
but
and
if you look,
that's of course a problem. The higher the bitrate, usually you get nicer ABX scores, while for something that closely resembles phonemes, you would have something very low bitrate. And if you compare, you can't compare two different methods without looking at that as well. So something that has lots of units usually also has higher bit rates, and then better ABX scores in the end. There's a sort of correlation, at least. In that sense, you would need to have some additional comparison in terms of the number of units or the bit rate, and that's true. And that is a weakness of ABX, I guess.
Yes, and actually the zero source 2020, everybody reported improvement on ABX, but as you mentioned, basically the bit rate. Maybe one thing also, I think ABX can still be valid if you compare. I think basically people should distinguish between feature comparison and discretization. So my task here is not eventually to output posteriors or to output features. It's really to provide a discrete representation. And maybe one drawback I was still seeing, and it's probably arguable, is like features and discrete representation, or continuous and discrete representation should not be compared at all, because it's just different things. So I was a little bit somehow skeptical about allowing to compare these two different things. But I think that the debate will go on, because I think you've given very valid arguments. So I cannot really counter them, but I feel also the ABX, or the zero source challenge, hasn't given any insightful result or exploitable result in terms of which direction we should go. And it's my feeling. It is very like a personal opinion here.
Thanks.
Thank you.
Yeah, I was going to ask, well, since Roger mentioned that in the chat, I was going to ask you about whether you can actually discover phonemes. And so, okay, let me step back a little bit and talk about the definition of phonemes. If you need to actually discover phonemes are used to basically distinguish or contrast meanings, well, words basically. And if you don't have any meaning or words, the concept of words, then basically you won't be able to discover phonemes in some sense. So I can give you one example. So in English, vowels are sometimes nasalized by accident because of co-articulation and so on. But in French, vowels are also nasalized, but the nasalized vowels in French actually differentiate words, but then the nasalized vowels in English does not differentiate words. So you cannot, just by changing one vowel, and basically you cannot nasalize one vowel in order to get a different meaning in English, but you can actually find that minimum pairs in French. And so the question is, if you don't know anything about words or meaning, would your system be able to discover phonemes? Does that make sense?
Good question. Yeah, no, I understand. I understand the distinction between phoneme, and I try to be careful to talk about phone or pseudophone in my context. And well, the difficulty in your question is if you requires, if we have no notion of phone, well, that seems difficult because the notion of phoneme is tightly related to semantic, right? So if you just have a string of phones or phones, not phoneme, well, it's hard to tell whether they are of sufficient to discriminate the semantics or not. So I would definitely say that to have the notion of phoneme, one need to have already the semantics or at least the words available. I don't know if that makes sense to you.
Oh yeah, it makes perfect sense. I mean, to me, I feel like all of the unsupervised acoustic unit discovery work. I mean, there's this limit, basically. If you don't have enough knowledge or other types of constraint, there is no way you can discover phonemes, basically.
But I think if we make a parallel with infants, when I was saying that actually this is a crude model of infant learning, it's a very crude model of learning because infants have several streams of input, have several sensory inputs. So we have speech, we have visual, we have sensation, touch, taste, and so on. And I think your question makes more sense if we start to add actually this other stream of information. So here I'm voluntarily not telling that we give the words. We would just simply add stream of information. In this sense, we can think that maybe the notion of phonemes can be the set of phonemes is eventually the set of sounds that are sufficient to properly react or properly learn the other streams. So maybe I'm making things a little bit more complicated, but if let's say that I only have picture and I have some basically I learn the acoustic unit and it's a multitask learning. I'm also learning to eventually discriminate images or similar things. In this sense, we may eventually be able to enforce the notion of phoneme because we may discover some phone in the data, but we may also learn that having two separate phones is not really necessary because it's enough for discriminate the image to just to have one sound representing them. So in this multi-stream / multitask scenario, I think it's actually quite likely that the system will basically get a sparser representation in the units.
Yeah. So, yeah, I totally agree with you. So basically, you need either additional supervision, while for infants, it's probably additional interactions with the world in order to actually discover phonemes. Yeah, that's just one question. Well, if no other people have questions, I can keep asking. The other one is... Oh, sorry. Somebody
Can I interrupt you, Hao?
Oh, yeah, sure.
I'll start by thanking you for organizing this, and thanks, Lucas, for an awesome talk.
Thank you.
I had a very quick question, also because I'll run in a bit. The one side comment related to this, because I find this super interesting, is that actually the baseline result you present somewhere where you have the David Horwath model and looking at that visual supervision is kind of getting towards including some semantics in there. So just a side comment. My actual question, it's a quick one. I think recently there's been a few studies on acoustic unit discovery where they've shown that these VQ models, neural models, can actually do quite well, especially if you train on tons and tons of data. And maybe my question is, if you think about the three motivations that you noted in the beginning, do you think it's reasonable that we might, to get close to that boundary that Hao was talking about, that we might need to train on 6,000 hours or maybe 60,000 hours of speech, and how that links in with the motivation?
So that's actually interesting that you mentioned this, and I think there are different schools. So I think it's right in your observation that if you start to just feed data, like obscene amount of data to the system, we might actually observe like interesting things like the formation of phonemes or like better categories. I took actually different approaches, and I saw that maybe we don't need that much data if we have transcription data. So in a sense, if you give me transcribed data, I'm learning faster, right? So maybe you need 60,000 hours of data for if it's unlabeled. Maybe I need this 100 to 100 if it's labeled. So I have chosen a different path and saying, well, if we want to be practical for the problem of endangered languages, we can somehow be faster using transcribed data because we'll need less amount. But if you remove labels, I think you do need quite some data. I don't know if you would agree with this view.
I don't have a very strong opinion. I think I'm more scared. of of having to buy humongous machines to fit everything in. So I haven't thought about this completely. I do agree with how that there's this kind of upper bound for how far you can get, even with phone discovery in a completely unsupervised way. But I just wanted to get your thoughts on whether the scale of the data is what will bring that solution.
But I think so I think it's pretty clear that infants are not learning from scratch. I mean, if we make infants are learning to speak with quite, I mean, we can still say that they have supervision, but sure, a kid who is born blind will anyway learn to speak, and that's a fact. It doesn't have visual signal, and it's quite impressive when we think about it. So it seems that it's quite doable, and with a reasonable amount of speech, not 4 hours, but still reasonable. But the question is how, and I believe there is quite some evolution basically has leave on trace in our brain, and we have quite some pre-trained. We are quite kind of pre-trained to hear speech. So I think if we want to avoid this basically upper bound of data, this limit of data processing, we should basically aim at a learning system using the data we have, transcribe and untranscribed data, to basically simulate this pre-training, this knowledge of speech, this a priori information, and then we should be able to learn without much data on any language. So at least that's what I believe. Where is the limit? I don't know.
Thanks a lot.
Thank you.
Anybody has questions? Well, okay, I'll just ask that quick question. So in your formulation, you have this embedding in your HMM. And then to me, it feels like it's a clever way of tying the parameters in your HMM. And so yes. Maybe the improvement is actually coming out of this clever way of tying parameters. Does that make sense at all? Because
that makes sense.
Yeah, let me add a few more comments on that. So you're basically using the embedding to generate the HMM parameters. And so somehow the HMM, each of the individual HMM parameters are tied at a higher level with your embedding vector, and obviously additional parameters as well. And so in some sense, I wouldn't say that the SHMM is strictly less powerful. I think in terms of capacity, it's really hard to tell, but the parameters is definitely tied in a very specific way.
Yes. So in terms of model capacity, it's exactly the same, because the acoustic model is exactly the same. So there is no question whether one is more powerful. They are the same. But it's a very important observation you make is indeed we tie the parameters, and this is and the benefit come from this definitely. We are basically relying on this. There is also one thing, and it's maybe very technical, so I will try, but I'm not sure it will be easy to explain. So in the previous model, I'm not learning the embeddings, but we are learning the Varchonal posteriors, which is fully factorized. Learning the embedding in this tie space, we still assume the embedding the posterior is factorized, but because, as you say, the parameters are tied, it's more or less learning a distribution with actually correlation between some dimension of the parameter space. So practically speaking, I do believe that even the Varchonal posterior approximation is probably better for the subspace HMM. But that's very technical, so I won't explain too much. Then I also want to say that the fact that you share the parameters, it makes the generalization better. So I would definitely assume that the SHMM, we haven't made experiments, so it's guts. I'm talking with my feelings, but I do believe that the subspace HMM would work even much better than the HMM in smaller amount of data, basically, because you have less free parameters. So in a sense, you should be happier.
Hi, Luca. I just wanted to add a small detail. I think in your presentation you had the fine-tuning experiment. So when you fine-tune the substrate
Should I show it?
I guess if you have it on.
Yes.
I'm pretty sure. So I was just going to mention that I think if it's just about the tying of the parameters does help things, but also what we transfer. Yes, okay. So I think if the difference between SHMM2 and SHMM is basically what we get from the kind of knowledge that we're imbuing, right? Because if it was just about the tying of the parameters, then SHMM2 should be as good as SHMM.
Yes, that's a good point. Yes. Well, I'll let you, sorry, finish, Balaji.
No, that's just what I wanted to say. I think you can maybe explain it better than I did.
Well, yes, so in this sense, in this system, basically it's equivalent to the HMM, except that the parameters are tied. But we see that even though we get some improvement, we don't get as far as when the subspace is fixed. So there are two things. There is a tying of the parameters, but so we give this improvement, let's say 2% absolute, but we also get some improvements by pre-training the subspace on unsupervised data, and then fixing the subspace. So the learning of other languages does help also. It's not just the tying of the parameters.
Any more questions?
Yes, good evening, Mr. Lucas. Hello.
Hello. Good evening.
I have a question. Actually, I am working on native language identification.
Mm-hmm.
Hello. Are you?
Yeah. I hear you.
I think this has got very direct relevance for that. Recently, I submitted a paper where South Indian languages can be clustered. English spoken by South Indian speakers. I have used the same MFCC features.
Hello? Oh.
Is it useful? Something.
Hello?
This same. Is it useful for native language identification?
I'm sorry, sir. The internet connection was very bad, and I couldn't hear your question.
Foreign accent identification. Identification. Is it useful? Foreign accent recognition.
That is interesting, actually. And so honestly, I don't have any experience on this. What I can let me share my screen again.
Because phonemes, it has direct relevance to phonemic organization.
Exactly. So here, what you see, I will simply re-explain. So do you see my screen? I will.
Yeah.
So I was going a little bit quickly here, but what you see here is learning the system. So here we have several embeddings for French, German, for all of the language. We have actually 4 embeddings. And what we did is we split each language data corpus in 4 parts, and we told the system they were different languages. And of course, they are going together because actually the acoustic is the same. It's coming from the same corpus. Notice, however, that here French is close to Swahili, and which is African language, and very far from German. So it seems that the distance is purely phonetic and not about, even though like French and German would have similar words, let's say French and Spanish would have quite similar words, but the phonetic of the language could be quite different. And in this sense, I believe that Swahili is phonetically closer than French. In a sense, I would hope that if now I have French, or let's say the example you were giving, you have English and English spoken by South Indian, I think you said. It's quite possible that the phonetic would be quite different from South Indian phonetic, because even though the words are the same, the phonetic might be drastically different. So I would believe that it will appear quite different in the language embeddings. So it's
yes, I have application also.
Yep. Hello. Hello.
Yes. 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 Hello.
I can hear you.
Yes.
I can hear you.
I got convinced. Yeah.
So everything is good?
Okay. Okay. Thank you.
Thank you. Thank you very much.
All right. I think it's fairly late, at least not here in the UK. I don't know. The meeting is fairly long right now. I think it would be nice to stop here. And obviously, if you have any more questions, I believe Lucas will be happy to answer them. And you can feel free to email him as well. And so, well, thank you all for coming. This is probably too late, but a lot of people have already dropped out. But yeah, so thank you all for coming. I'll announce the talk. So the next one will be 2 weeks from now, and it's going to be about a completely different topic, speaker adaptation. So stay tuned. Thanks again, everyone. I guess I'll see you 2 weeks later then.
Thank you very much. Bye-bye.
Bye.